Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with liquid extraction. So just to remind you guys, before midterm we have discussed absorption in this subject. We discussed absorption in detail, absorber design for various systems and by using various methods. This was already discussed in the start, before midterm. So one thing I want to advise you, please just don't forget that syllabus, just go through that, and like you had vacation of almost I think 3 months, so definitely I think you have forgot many things, so I will advise you to just go through that, because at the end of this semester now we are going to have comprehensive exam, so you have to go through all that. So let's start with this topic, liquid extraction. So in this lecture we will get familiarized with liquid extraction and its basic definition, what liquid extraction is, what is methodology followed in liquid extraction, or steps involved here, then why we prefer this liquid extraction over other techniques like distillation, absorption, stripping, or what are some basic terminologies and example related to this liquid extraction, like industrial example, and there will be something called solvent here, so we have to discuss what kind of solvent should be used in this liquid extraction. So just to start with its introduction, we will just go through the definition. So hopefully you all are familiar with this, because we started at the start of semester in a brief way. So liquid extraction is actually also called solvent extraction. So liquid extraction is also named as solvent extraction, because here what you do, you extract something from the solvent or with the help of solvent. Liquid extraction here will involve actually a liquid feed in which there can be two or more than two components. One of the component here is feed, which again consists of sometimes two or more than two components. What we do, we bring this feed which is in the form of liquid and which contain two or more than two components. It is brought in contact with a second liquid phase called solvent. When you will bring this feed in contact with a solvent, what happens actually, some components of this feed are immiscible or only partly miscible. What does this mean? It means that some components of your feed, they are soluble, they are miscible, while others are immiscible with the feed. As he mentioned here, that more or sometimes with one or more feed components are completely or partially miscible with one or more components of feed component. So overall, what does this mean here? That liquid extraction is a technique in which you bring your feed in contact with some other solvent. Now your feed consists of actually two or more than two components. So out of those two components, one of the component is immiscible with this second introduced solvent, while one of that component is miscible or completely miscible with this externally introduced solvent. So with this, what will happen, that component which is miscible will be transferred to this solvent, that will be separated from its feed, so then you can just on later stages can get it separated from solvent too. So solvent is recovered and that is sent back to this unit to be used again and again. Why he mentions here that some are immiscible, because our purpose here is to separate your feed into two parts or maybe sometimes more than two parts. So here we just consider that we have to separate into two parts, so some of those components will be transferred to the solvent, while some will be left inside feed. So for example, we discussed this, that hydrocarbons, like if you have benzene and phenol and they are present in the water and we want to remove them or we want to separate them, what we will do, we will bring just any other hydrocarbon in contact with this. Suppose we just bring some alcohol or anything. So what you will do when you bring that component, that solvent in contact with this feed, which consists of actually this any hydrocarbon plus water. So what happened, you know, definitely these hydrocarbon will have more affinity towards newly introduced hydrocarbons. So with this they will be transferred to that, they will be miscible with that, while this water will not be completely miscible, or it will be like partially somehow immiscible. We should select actually such solvent which has no affinity for this component. So any of this component, like here we have water, so in that case water will not be transferred, that the hydrocarbons will be transferred towards that liquid and they will get separated. So when you look at liquid extraction, actually it involves some steps which are necessary, or which are the stages required for this operation. So what are those stages? Actually liquid extraction involve first stage, that what you have to do, as we just discussed, that there is something called feed and other is solvent. So you have to bring them in contact with each other. Like you have feed here is actually solution, because that contain more than one component, so due to this he is calling it solution. So you have to bring this solution or a feed in contact with the solvent. So when they come in contact with each other, so what happens, they get mixed with each other. You just shake them, you mix them by applying centrifugal force or mixing, and after that you give them some time, so they get settled into two separate phases. After mixing, like for last example, when you have these hydrocarbons plus water, any of hydrocarbon, we just consider, suppose we have phenol and water, and then we bring it in contact with the other solvent, another hydrocarbon, and we mix them. After that we give them some settling time. So when you will give them some settling time, actually due to the density difference, they will be separated into two phases. One will be the top layer and other will be the bottom layer, and out of those, this top layer, that is actually the lighter component with low density, so that's called extract, while other is called raffinate, that is the heavier one with a high density, which will be the lower one. So after this, what we do next purpose is actually here this extract is lighter phase, that will contain solvent as well as one component extracted from this feed. So this is separated, actually that separated finally to recover your solvent, so that can be used again here in this process. So that's the last point, like here removal and recovery of the solvent from each phase. Suppose if some of the solvent become part of this raffinate, definitely we also will go for the separation of the solvent, so that can be used again here for extraction purpose. So this is example of this liquid extraction technique used on lab scale. Here you have in your lab one experiment, maybe you have performed or maybe performed later if university opens. So here liquid extraction, actually in this what we do, this is called separating funnel. So in this you can see this is your feed, like that feed contains two components, just they are just separate, shown here with the separate colors, like one is of blue color and other is of like black color. So just consider them like two miscible liquid. This is feed, as you discussed that your feed will consist of two or more than two components, so here just consider that it contains two components. Now what is your purpose? So just look here that our purpose is to remove this black color liquid from here. They are actually just shown here in the form of dots, actually it is liquid, don't consider it like solid particles. These are like just two color liquid. In order to show them differently, they are just shown in such a way. So what you do here, you just bring some other solvent in contact with this, and that solvent actually will extract. The purpose of that solvent is to extract these black color dots or black color liquid from this mixture or feed towards itself. So what we will do, actually we will be just separating this black color liquid from the blue color liquid. So when you bring this another excuse me so when you bring here this new solvent in contact with this feed, what you will do, actually here one step is missing. Here you will bring them in contact, you will shake them, you will mix them, and then you just give them some settling time. When you will give them some settling time, definitely they will be just settled down into two separate phases. As you can see here, the one is called raffinate and the other is called extract. The lighter one with low density is extract, and the heavier one with the high density is raffinate. That will be definitely present at the bottom here. So now you can see here what happened actually. If you look at the difference, this black color liquid is majorly transferred, as a large part is transferred to other introduced solvents. So by this, now you will just separate it down. As we discussed here, we said that extract will be separated and then it is removed. Actually this solvent is further separated from this liquid, black color liquid, so that it can be used again here in this stage. Another example here is like if you have more than two components in the feed, because we said that in the last example we have two components, but here you can see you have actually three components in your feed. So what you are doing here, you are just bringing another yellow colored liquid in contact with this. When you bring that liquid in contact with this, so what happens actually, you can see that that component is highly miscible with one of the components of the feed, that is black color liquid. You can see that when you bring them in contact with each other and you give them some settling time here, I mean you will mix them and now you give them settling time. After settling, they get separated into the two phases, and out of two phases you can see here that this black color liquid has more affinity for yellow color liquid, and that is transferred to that, while some part of also this another liquid is transferred, but in very small amount. So it happens actually in reality when you bring in contact with some solvent with your feed. So definitely all of those components are feed are transferred somehow, but one of those components is transferred in the major amount, in large amount. So that's our purpose, is actually to bring such solvent which can extract one of the components from your feed which we want to separate. So after that, what you will do, just you will open this stopper and you will get them separated on the lab scale. So here when you get them separated, later you can use it, or you can bring it to some, or send it to some next operation in the industry. While here you can see that this solvent that contains this black color liquid, we also have to separate it. So we will just collect it, we will then go through some other operation, maybe distillation or crystallization, any other operation we will just discuss later on in one example. So the purpose here is actually to separate now this solvent from this extracted component. So when you get your solvent extracted from this component or separated from this component, you will bring that solvent again here and can reuse it. So this is just overall view of the liquid extraction, that what happens or how it is carried out. Just to summarize it, it is carried out in three stages. The first step is to bring in contact your feed with the solvent. So when you bring them in contact with each other, you mix them, then you give them some time for the settling, so they get settled into actually the two separate phases. One is called extract and other is called raffinate, and then finally where we go for the removal and recovery of the solvent, because here our purpose is to reuse the solvent, so we will just recover it so that we can use it again. Similarly here extract and raffinate for this stuff. So this solvent which you have discussed here, solvent as we said, here you can see it actually one color liquid in the last example, so that shows that it is pure component. So but this liquid can also be solvent, so which you are using here for extraction purpose, so that can be a pure component or sometime it can be a mixture. So it depends on your requirement of the system, that either it should be pure or maybe sometime it is mixture. So there is another terminology used also in parallel, or we have to discuss this by the way at the end of this semester, I think in the last week. So leaching. Leaching is solid liquid extraction. Actually here we are discussing liquid extraction in this lecture majorly, but just to introduce you or to differentiate between these two. So this definition is provided here for solid liquid extraction or leaching. So this involves actually the recovery of a substance from a solid. Actually here your feed is solid in this case. In liquid extraction, your feed is a liquid and you bring it in contact with other liquid, that is the solvent, and then some of the component are feed are transferred to the solvent and you get them separated. But here in solid liquid extraction, actually you are recovering the substance from some solid. So when you bring this in contact with some liquid solvent, so what will happen, it will extract some of the components of the solid. Some of the components of solid will be transferred to this solvent, and then we later separate this solvent again and reuse it, as we have discussed in the case of liquid extraction. So for example, here recovery of oil from seeds by organic solvent. What you do, you just bring, as you know that various seeds contain various kind of oils. So oils are majorly like somehow organic in nature. So if you have to separate them or you have to extract them from the seed, what you will do, you will bring your seeds in contact with some organic solvent. Now when you bring it in contact with organic solvent, what happens, that organic solvent will definitely attract those components which are of same nature, like they are organic in nature. So from those seeds, organic components will be extracted toward this organic solvent, which was introduced as a liquid solvent from outside. So when you just extract those hydrocarbon or organic chemical, organic components to this organic solvent, they get separated from the seed. So this is called solid liquid extraction or leaching. Like as well, we have here extraction of tea from the tea leaves or beads using hot water. This we discussed actually in the start of this subject. If you remember, at that time we discussed that there are various separation technique, and all of those techniques which we are going to discuss throughout the semester, we just discussed briefly, one or two lectures. So there we discussed this example of extraction of tea. What do? You just put either tea leaves or bead in the hot water, or even in the cold water if you put them, but they are not extracted in large amount. But if you put in hot water, definitely it is extracted in large amount. So what happened here, from the tea leaves or beads which are in the form of solid, some components are extracted towards the liquid, and liquid is here hot water. So that's also like solid liquid extraction, or this technique is named as leaching. Okay, now when you are aware with the liquid extraction, its definition, its basic principle are like operation and its stages. Now when we use this liquid extraction, because there are some widely used operation, as we know that distillation is widely used, and then after distillation we have discussed that absorption is used on large scale, but sometimes also liquid extraction is also used in some cases. So when we use liquid extraction, one thing I want to convey here is liquid extraction is actually used in combination with distillation for some purpose to separate some component. Actually in those cases, maybe distillation is not feasible one or not economical, so we go for other technique, that is liquid extraction, and then some part distillation will also be there, or sometimes this liquid extraction is used in combination with like absorption or sometimes crystallization. So there are various ways in which it is used. But when we use, especially like here, when you have such component that they require excessive amount of heat or very large size column, when we go for large size distillation column, when the components are like large size, means they are that contain very large number of plates. When components have actually close volatility, or their relative volatility is near unity, so in this case actually it is difficult to separate those components with the help of distillation. Difficult in terms of you will need very large column, large amount of heat. So in such cases it is better to go for liquid extraction. Now the two components which you want to separate, and they are close in boiling point, they have close volatility, so you will bring some other component, some other solvent which has better affinity with one of this component of the mixture which you want to separate. So in this case, that component which has affinity with the external introduced solvent, that will be transferred and you can easily separate them. The other option, second option in which you go for liquid extraction, that's the formation of azeotrope. As you know that in case of azeotrope, again you can't separate your liquids by distillation, it is difficult. So in this case, definitely again the better option is to go for this liquid extraction. So in this case you will do, again you will bring some component, external solvent which has a better affinity with one of the component of the azeotrope, so it will just extract that component from azeotrope, and azeotrope is separated, that mixture is separated. Next, when heating must be avoided, sometimes you have heat sensitive components, so in order to avoid this uh, destruction of those components, we don't want to add heat, we don't want to go for distillation, so you can go for liquid extraction here to separate those heat sensitive compounds from each other. And when the component to be separated are of quite different in nature, for example, sometimes if you have hydrocarbon mixture, but that mixture is such that like it contains sometimes paraffinic, aromatic and naphthenic or such kind of components. So what you see here, they are all hydrocarbon, but they are of different nature, and suppose if you have to separate them, so it's better to go for liquid extraction instead of distillation, because suppose you have some of those components, definitely they are hydrocarbon, they will be close in boiling point to each other, their volatility maybe will be close to each other, so it will be difficult to separate them. So it's better to go for this kind of technique that is called liquid extraction. And then there is high boiling component present. Yes, this is another thing, like maybe not related to the, all those are related to petroleum, so this is somehow related to petroleum, or sometimes can be applied to other industries too. So like here, if we have a high boiling component present in relatively small quantities in an aqueous waste stream, so what does this mean? It means you have some component, just consider for example acetic acid, and that is present, acetic acid actually has I think boiling point of around 118 degrees centigrade. So if it is present in very small amount in water, so now in order to separate this from water, you can go for distillation, right? But if you go for distillation, now you have to separate water from this, so water is present in large amount, as he said that that component is present in high boiling component is present in small amount in aqueous waste stream. It means major component is aqueous stream water. So now in this case what will happen, if you go for distillation, you have to add very large amount of heat to boil this large amount of water to get that separated. But instead of this, then for going for this very expensive process of heating, you can go for liquid extraction. What you will do, you will bring some of the component which has better affinity for acetic acid, as we are considering in this example. So you can just extract, or you can remove that small amount of acetic acid in a more economical way by using this liquid extraction, as compared to that distillation, which will involve very large column as well as very large amount of heat. So here he has provided that, like for example, recovery of acetic acid from cellulose acetate, that will also be the same way, like that is present in the cellulose acetate and it is present in very small amount. So if in order to remove this very small amount of this acetic acid, so what you will do, you will just go for liquid extraction instead of distillation. Right. Now up to here, you know, okay, where we can use or in which conditions it is better to go for liquid extraction instead of like distillation or other process. So definitely there will be a question in your mind that then what are important applications of this liquid extraction. So most important application of this liquid extraction are actually separation of aromatics from kerosene based fuel oil. You know that kerosene based fuel oil, if that contain aromatics are actually, they cause it is difficult to burn them, so it's better to remove them from kerosene, that we can burn it more easily. So if you want to remove them now, aromatics and also kerosene, because kerosene is a mixture of hydrocarbon, so those hydrocarbon are actually mostly in I think straight chain, as well as if they are rings, they are saturated one, but aromatics are unsaturated one. So now we have to remove them. In order to remove them, if you go for distillation, definitely you will be boiling all of them because they are close in boiling point, so it's better to go for liquid extraction. and this is one of the wide application of liquid extraction in this industry. As well, there is separation of aromatics from paraffin and naphthenic compound to improve the temperature viscosity characteristics of lubricating oil. So what is purpose here? To remove aromatics from paraffinic and naphthenic component, and what you will do there, you were just in last example, you are improving the burning quality. Here actually our purpose is to improve the temperature and viscosity characteristics, because you know all these are hydrocarbon but they have different characteristics. So if aromatics are present in this lubricating oil, which are actually formed of paraffinic and naphthenic compound, so they will cause some trouble. They will have these characteristics of temperature, viscosity, they deviate from your required one. So what you do, just you go for liquid extraction to get them separated from this mixture. So finally when it is separated, definitely your characteristics are improved. Right, so here first large scale extraction process which was used in the industry in 1930, and that was related to these example, that is actually removal of aromatic and sulfur compounds from liquid kerosene. And here the solvent which was used for this purpose was liquid sulfur dioxide. So what you do, you just bring your kerosene, which contain actually all other hydrocarbon required one as well as aromatic and sulfur compounds. So you bring it in contact with the liquid sulfur dioxide, and that will extract the sulfur compound and aromatics with them, and this kerosene will get separated or get rid of these impurities. Right, when you go through this liquid extraction, so there are some terminologies used in this like related to something called carrier, solvent, stages in liquid extraction. So let's discuss those terminologies so that you can understand them properly. By the way, one thing here I want to mention, that liquid extraction which we are going to discuss in this chapter or throughout the lectures here, that is ternary system. So what is ternary system? Ternary is related to three. Mean liquid extraction by treating a ternary system. Ternary system mean that system which consists of like two miscible components, like your feed. As we said, that feed can consist of sometime two components, sometime more than two components. Like here we will just consider that it contains two miscible component. Out of those, one will be called as carrier and other is solute. Like for example, if you consider benzene in the water, so benzene is in very small amount, that is solute, and this water is considered as a carrier here. I mean water will be carrier and benzene will be solute. So we bring this in contact with some other hydrocarbon, solvent, pure component. So here your solvent is a pure component, one component. So overall you can see here the two component of the feed and one this solvent. This is ternary system, which will involve two feed component in the feed. One is the carrier, which is in large amount, which is carrying other solute, which is in small amount. They are actually miscible with each other, they are mixed with each other, they are soluble with each other. When you bring them in contact with the solvent, which is pure component, externally introduce solvent. So what will this solvent do? This solvent will just extract this solute A from this carrier, and it will carry away with itself. So when we look at this system mean, that is carrier, solute and solvent, what is your purpose here? Just think for a minute, like our purpose. What is our purpose? Okay, hopefully you know that our purpose here is to remove this solute, as I have discussed, that to remove this solute from this feed, to get separated this solute from this feed. So it's mean that your solute should be miscible with the solvent. This solute should have affinity for the solvent. So when we have to select the solvent should be of such nature that it can easily attract this solute from this feed, but this should not be miscible. This should not attract a large amount of the carrier. Although you can't avoid it completely, mean when you go for such systems in a liquid extraction process, definitely you will see that some part of the carrier is also extracted, but major part that should be extracted is this solute A. So here your components C and S, mean this carrier and S solvent, are at most only partially soluble. They should be either insoluble with each other, or they should be like partially soluble with each other. That means only small part of this carrier should be transferred with the solvent. But this solute A, as our purpose was to extract A from this feed, so this solute A should be completely or substantially in large amount should be soluble in S, that should be attracted towards S, so that can be separated. So now when you look at this separation, like you want to remove this solute A from the solvent, so when we go for this, you will look that there is not only one stage, you will need more than one stages to remove or to completely extract A from the this feed towards solvent. So you can look here at this example, that like in the first stage what you are doing, you are just bringing your feed, this solution means feed actually, that is consist of carrier and solute A. You bring it in contact with the solvent, you mix them, as we have discussed that is the first stage, that you have to bring them in contact with each other and mix them. By mixing actually you increase the mass transfer of this solute A from this feed towards solvent, and then we give them some time so that they can get settled in the form of two separate layers, as you have seen in the previous slides. So they get them separated into extract and raffinate. Raffinate is the heavier stream that will be at the bottom, and extract is the lighter one. So now you see here that after this it is not finished, still it's going on. What you are looking at this here, raffinate go to another mixer. In mixer 2 what you are doing, you are again introducing some of that solvent, and this raffinate is actually feed. That raffinate contains carrier as well as some amount of solute, because in this stage, in first stage, all amount of solute is not transferred towards solvent. So when you go for the second stage, in this raffinate it will contain carrier as well as some amount of solute. So you will go to this stage, and when bring in contact with next fresh solvent, it will extract more solute from this feed, and again after mixing you go for settling, and in this separator you can get separated like extract and raffinate, and maybe you can go to next third stage, mixer 3, and so on. So it depends on your operation, that how much purity you want, or how much amount of solute you want to separate from this system. The stages, these stages are provided by actually the mixer settler units. Mixer settler unit mean it will contain mixer and then settler. Like here you are looking at this, that there are mixer and then there are settler, and mixer settler, and so on. Sometimes we have columns with mechanical agitation or centrifugal devices. So there is actually not two units, there is one unit in which in column you have some mechanical agitation, you have some mixer. So mixer, what does that mixer do? Mixer will mix these solute and solvent coming to that unit, like solute and solvent when they are coming to that column, they get mixed with each other, and after that you have some mechanism in that same column that they get separated based on density in the same unit. Or sometimes maybe you can just after mixing you can bring them to the next settling unit and get them separated into two phases, and then you go for next further process. So up to here I think now just briefly to refresh you that we discussed, or to remind you what we have done so far, that we discussed or introduced you to the liquid extraction definition. Then we switch towards basic phenomena, how this liquid extraction takes place, what stages are involved, and how does it look on the lab scale. Then we discussed then in which cases or when it is preferred, or when you go for actually liquid extraction instead of other technique like distillation, absorption, stripping, or crystallization, or any other separation process. So Majorly we have seen that this is used in petroleum industry, in which actually what you do, you are just separating some of those hydrocarbons from the other hydrocarbons. As well, then we saw that major application of liquid extraction that was initially used, that was in 1930, and was being used again in the refinery or petroleum industry, in which you were separating some of the unwanted component from kerosene. And then we have just seen this definition. Now what is carrier, what is solvent. You know that your feed contains these two components, that is, one is carrier and other is solute. For example, you have water and benzene, so benzene is solute and water is the carrier, and you bring it in contact with some other solvent like hydrocarbon, so that is the solvent. And then ternary system, this is actually ternary system in which there are two components in the feed and one is solvent introduced from outside. So let's start from here, one industrial example of liquid extraction. Before we go for like liquid extraction, I want to just tell you that here liquid acetic acid is produced from various methods. Like here is methanol carbonylation, and then there is acetaldehyde oxidation, or as a byproduct of cellulose acetate manufacturing. So either of these three processes, when you go for them, just look at the detailed equation if you are interested through the literature, that what reactions are take place and which products are produced and how it is produced. So but our purpose here is not to look at those reactions. Actually our purpose is here that in all of these cases, when you will look at main reactions or the system, so you will see that there is a mixture of acetic acid with the water. In all these cases, a mixture of acetic acid is produced with the large amount of water. So like here, acetic acid, which has a boiling point of 118 degrees C, and water has 100 degrees C, they come in the form of mixture, and our purpose is finally to get glacial acetic acid. Glacial acetic acid is acetic acid which is 99.88% minimum. What does that mean? That it will only contain 0.2% impurities, but 99.8% will be acetic acid, that is called glacial acetic acid. So now in order to get this glacial acetic acid, what you have to do, you have to separate it from water. And now, as we have discussed few slides back, if you recall, what option we have here to separate this acetic acid from water? Just think over it. Okay, maybe you can say distillation. Can we go for distillation? Yes, they have somehow a difference of 18 degrees C boiling point, so we can go for distillation. But the problem here is, actually, as we have seen in last slide where we discussed when we have to use liquid extraction, so there you have seen that mixture, when it contains less than 50% acetic acid. What does this mean? It means very large amount of water. More than 50% is water and less than 50% is acetic acid. So in this case, separation by distillation is costly due to high heat required for the boiling of water. Now because here acetic acid is 118 degrees C, so definitely water has less boiling point. So what you will be looking for, if you will go for distillation, your purpose will be to heat and just boil all of the water and get separated from this acetic acid. So in order to provide very huge amount of water, boil huge amount of water, distillation will become difficult. It will involve large amount of heat, so definitely it will become costly. It will not be physical and economical process. So then better one is to go for solvent extraction, liquid extraction. So let's look at this here, that this is the process of this separation of acetic acid from water, and our purpose is finally to get glacial acetic acid. So don't start reading it, please, just proceed with me. Here you can see that this is the first unit, which is your actually the extraction unit or liquid extraction unit. So in this case, what you are doing, you are just bringing some feed. Here you can see this is the feed which contains of actually acetic acid and water. So here these are the flow rates, which are in, I think, pound per hour. Yes, here it is mentioned flow rates are in pound per hour. So here you can see that water is like, I think, 4 times higher than the acetic acid present in this system. So water has boiling point of 100 while acetic acid has 118. So as we said that when water is present in more than 50% amount, so a distillation is not feasible one. You have to go for liquid extraction. Due to this we have brought this system here. So next here, when you have to remove this acetic acid from water, so you are going for extraction process, liquid extraction. So what you will need here, you will need some solvent. We have to bring some solvent in contact with this feed. So solvent used here is actually ethyl acetate. From where we are introducing, from here you can see this recycled solvent that contains actually the water and ethyl acetate. So here your major component used for extraction is our solvent is ethyl acetate that has a boiling point of 71 degrees C. At these are actually given at normal boiling point, given at atmospheric pressure. So you bring them here. You can see here that when you are bringing solvent, solvent contains some amount of water, that is 2500 pound per hour, while major amount is 68,000 pound per hour of ethyl acetate. This is one of the main system in which you are just providing here some mixing with the help of mechanical agitation. We are just mixing, rotating this main system in which there will be disc inside this. You can see in your book details are given that it contains, like I think this is 5 meter high and so on. Some other details are also given that there are discs. Actually when this will rotate, those discs rotate and this your feed will come in contact with your solvent. So when they come in contact with each other, definitely acetic acid will be extracted or will be attracted towards this ethyl acetate, and that is transferred from this towards ethyl acetate. When it is transferred towards ethyl acetate, so at the end, if you give them some settling time, so here they will be just separated into two phases. As you know that those two phases are, one is extract, that is low density solvent rich stream. Low density solvent rich solvent, our solvent here is ethyl acetate, that is lighter as well. It will contain acetic acid, so that is one which will be at the top. So here this is extract, that contains actually majorly ethyl acetate and acetic acid. One thing you can see here, that it also contains water. If you remember, we said that our solvent should be of such nature that attracts more amount of acetic acid, or like more amount of solute which you want to separate, and small amount of other component which is carrier. Actually carrier here was water. You can see that water was present in very large amount, 23,000 pound per hour. That some amount of this, definitely 6,000, is attracted towards this. But if you see here that the acetic acid was 6,660 pound per hour, and this attracted towards this ethyl acetate is 6,649. It's mean almost almost you can say 100%, not it is 100%, okay, just say 99% of this acetic acid is to transfer towards ethyl acetate. So what was our purpose here? To get it separated from water. At least it is, we get rid of this from water. It is transferred now towards, let's say, this ethyl acetate, which is solvent. So now next thing which I was talking there, that it is used, actually liquid extraction is used in combination with other techniques. So here you can see that like you have this mixture, actually that is ethyl acetate, water and acetic acid. Our purpose here is to separate, or at the end to get glacial acetic acid here. So in order to get this glacial acetic acid, you have to separate it from this ethyl acetate and water. So what you do here, you go for next stage, and that is okay. Before going to next stage, I just want to clear these two phases. One is extract and other is raffinate. Raffinate, you know, that is high density carrier rich stream. Carrier here was water, so you can see that carrier rich stream is here, that contains, carrier rich means it will contain large amount of carrier. So here it contains 19,000 and something like pound per hour of water. So that's the raffinate one, high density stream, that is at the bottom of this extraction unit. So just proceed with this. The first one, extract. In the extract, our purpose is to get rid of ethyl acetate and water and get separated acetic acid, which is our product. So what you do, you go for here distillation unit. So you can see that this extract stream is moving or going to this distillation unit here. So when it enters to the distillation unit, definitely it will be get separated into top and bottom stream. So now look, just think for a while that which of these components, there are now three components: acetic acid, water and ethyl acetate. Which one will go to the bottom and which one will go to the top? Definitely the lighter one will go to the top and the heavier one will go to the bottom. Like acetic acid, which has a boiling point of 118 degrees C, we have this at the bottom, and our purpose is here to design such a distillation column which can provide you finally at the end of the day 99.8% pure acetic acid, that is glacial acetic acid. So when you go for this separation, finally you will be getting glacial acetic acid from the bottom stream. But at the top there will be a mixture. That mixture is actually two components. What are those two components? Yes, they are not acetic acid, they are ethyl acetate and water. So at the top of the column, you know that you have some condenser. So here we have a condenser. This will condense these liquid, and when they are condensed, so after condensation you bring them to some decanter. Decanter is a vessel, settling vessel that provides you separation based on density. So now this was a mixture when it was coming from the distillation column, and mixture of ethyl acetate and water which came from here. So acetic acid you have already removed, these two come here, they get condensed, they get to desiccator. So when decanter, in this decanter you get them separated into two phases. What are those phases? One will be water and other will be ethyl acetate. Now which one is the lighter? Definitely ethyl acetate. So ethyl acetate will stay at the top and water will be at the bottom. Now before proceeding for this water rich stream, definitely there will be not like complete 100% separation. This due to this reason he is calling this stream water rich. Water rich means it will contain majorly water but small amount of ethyl acetate, as well as at the top you will have ethyl acetate rich stream. So this ethyl acetate rich stream go back to the, actually this is our solvent. We have to bring it back. Our purpose is to recover this solvent and bring it back to the extraction unit. But you get that separated into two parts here. One will go for reflux of this tower distillation column, and the other major portion will go to the extraction unit. Now you can see here that it get mixed with some makeup solvent. Definitely we will have to have a makeup, because so sorry, I just forgot to mention this. So here actually two liquid phase separated in decanter by gravity, as I already told you, and then this ethyl acetate rich stream is divided into two. One is reflux and other is going to the extractor. Along with this, actually we have to make up some solvent, because all solvent is not recovered from here this system. Some solvent will go to this water rich stream, all is not coming back. So here in this case we have to make some makeup. Always in industrial operation you go for makeup. So that will be added here, and again this process will repeat. Now let's look at the bottom one. Before going to the bottom distillation column, you see that from this decanter you had one stream, that was the bottom of decanter, and that was rich in water. So you see here that is coming to this distillation unit again. Actually this is not only water, there is some amount of ethyl acetate present in this. So we want to recover that ethyl acetate still. Due to this we are bringing it to this distillation unit. In this distillation unit at the same time you are also bringing some raffinate, that is majorly water, but it also contains ethyl acetate and very small amount of acetic acid. So major is actually here ethyl acetate and water, and this water rich stream will also contain majorly water as well as ethyl acetate. So what you do, you just bring it here to the distillation column. Distillation takes place, and again here when you go for distillation, water is now heavier one. Here you have two major components like water and ethyl acetate. So water will leave this column from the bottom of the column, while at the top you will have it actually ethyl with acetate. So what happens here from the top, majorly there is ethyl acetate and very small amount of water. So what you do, you just give it some settling time again here in decanter. So in this they get settled actually, and after this you can bring some part as a reflux to the tower, while other is actually, as it is ethyl stream, so you just bring it to the two-phase separating unit. Why we are bringing here? It is ethyl rich that contains majorly ethyl, but this still there is some amount of water. So due to this, you are bringing it into decanter. So here, as you know, that in this decanter again, due to this separation is taking place, and out of this ethyl acetate will go back to the column, and water containing stream will go to this distillation column. So this is one industrial example, and here we have mentioned that makeup ethyl acetate solvent is provided for solvent losses to the glacial acetic acid and wastewater. Here definitely wastewater will contain some amount of ethyl acetate, as well as this is 99.8%, so it will also contain some amount of ethyl acetate. So in this example, finally to summarize, you can see that there is one extraction unit. In this extraction, what we did, we separated acetic acid from water, and then when it is separated from water, it is actually transferred to some other solvent, and that was ethyl acetate. So next purpose, our purpose was to get it separated from this solvent. So you go for some distillation unit in which you just separate this acetic acid, which is your main product, from this ethyl acetate, and then there are further processes. So liquid extraction is actually, when you look at this technology, it is a reasonably mature operation, but not like as mature as there was distillation, or we have discussed absorption and stripping. So if you remember, when we discussed absorption, we said that distillation is the best technology. Then there is absorption, actually in form of technology maturity, best in form of technology maturity, that they are being used for a very long time. So definitely they are good, and many companies are working with them, and so on. So this procedure for determining the number of equilibrium stages to achieve a desired solute recovery are well established. When we look at liquid extraction, we have seen few slides back that sometimes you will need more than one stages. So these stages, determination of various stages, equilibrium stages, is well established one. I mean, for that we have well established technologies, but for calculating equilibrium here, for liquid phase equilibrium, like simple limiting theory, like you have discussed Raoult's law for absorption as well as distillation. So they are some well established theories, but here in liquid extraction, for calculating equilibrium, for equilibrium calculation, we don't have such well established theory. So due to this, when you don't have any equation or theory like correlation, so definitely you know that you have to go for experimental data. That is preferred one for activity coefficient correlations. So here in this actually in this slide, you are shown with some solvents. So just look at this before we proceed towards table. Okay, actually in petroleum industry, application to separate heat sensitive as well as closely boiling component, you go for liquid extraction. Now in petroleum industry, you know that there are hydrocarbon majorly. So in order to separate those hydrocarbon, definitely you have to bring some hydrocarbon. Suppose, just look at this table now. Suppose you have benzoic acid that is present in the water. Water is the carrier, so benzoic acid is the solute present here. So you can see what you are bringing here, benzene. You are bringing here benzene to get it separated. As well, there are like fatty acids, and they are present in the oil. If you have to separate them, you are bringing some solvent actually, which is propane. Like next, in biochemistry industry, that's also liquid extraction is widely used, including the separation of antibiotics and recovery of proteins from natural substrates. So you can see here, I think, few examples related to this, but majorly they are, yes, majorly here in this table they are discussed of like, yeah, at the end, yes, you can see here that there is a vitamin A, and if you have to just extract it or separate it from fish liver oil, so what you do, you bring some propane here, like your propane will extract vitamin A from this carrier, and then they get separated. So these are example of this biochemistry industry, these vitamins stuff. And then there is also they are used in liquid extraction is used for metallurgical techniques, in which you actually separate various metals from each other by using this technique. As well, they are used in nuclear industry, sometimes to remove some specific component from spent fuels, or like that application, as well as in other industrial inorganic chemical industry, like sometimes we have we use them in acid industries or some other industries you can explore. Yes, the last part here actually in this table, no need to remember all this stuff, just you should know few of those, but you can see here solvent text, you can see that there are various solvents being used. So solvent is very important, because why it is important? From last discussion you remember that solvent should be miscible, that should carry some component of feed with itself, not all component, like it should only contain or only extract solute from the feed, not carrier. So due to this it is important, its selection is very important. So that's solvent in addition to be stable, non-toxic and inexpensive. First of all, it should be stable, it should not be reactive with the components of the feed. Like you have to select such solvent which is stable, which is non-toxic, which is inexpensive and easily recoverable. This is also necessary because we have to reuse it, so it should be easily recoverable. A solvent should be relatively immiscible with the feed component other than the solute. It should not be widely miscible with the carrier. It should only be miscible with the solute, so that you can easily separate that, and it should have a different density from the feed, yes, to facilitate phase separation by gravity, because you have seen in all example we said that we have to separate them into two phases. So in order to separate them into two phases, your carrier of the feed and your solvent should have greater difference in the gravity, so that they can be easily separated out. And then solvent must have a high affinity for the solute. Yes, this solvent should have high affinity, not like partial affinity. It should have high affinity, so that you can easily extract them from carrier, from your feed, from which. And finally there should be uh, ability for this to get separated from that solvent. This solute and solvent should have greater affinity with each other, but still they should be easily separated by distillation, crystallization, or maybe some other technique like absorption, or you can say stripping or any other technique. So why? Because you have to recover this solvent and you have bring back to the extraction unit. So it should have initially high affinity for that, but when we go for its separation, definitely they should get separated from any of these techniques. So that's it. It was about the introduction to liquid extraction, that in this what you just separate one of the components from your stream, from your feed, and there were some common examples of liquid extraction. Then we said solvent is very important, what kind of solvent should be there, and how it should behave with a carrier as well as our solute, that it should have affinity for the solute, but at the end it should get separated when we want to separate it. Bismillahirrahmanirrahim. Assalamu alaikum. Hope you all are fine. So before I start this lecture, a few things I want to discuss. First of all, I'm sorry for this background noise. Actually it's laptop fan, so I'm trying to overcome this problem. Hopefully by next week we will be in a better position. So I'm again sorry. Just try to use hands-free or headphone when you are listening to lecture. Right. Yesterday we talked about liquid extraction. I have introduced you with the liquid extraction, and today we have to go further with the liquid extraction equipment. But before I proceed with this lecture, I will just quickly recap the yesterday's lecture. So yesterday initially I talked about liquid extraction, that this is the technique which involves extraction of any component of a liquid which is a feed. Actually in our feed there are more than one component, and you want to extract one of those components from that liquid with the help of externally introduced solvent in the form of a liquid. So in this technique we remove some specific components from feed which are desired one, which we want to separate. So the external liquid or a solvent you introduce, that will extract some of the component, that will some of the component of the feed, while other component will stay as such in the feed. So later we talked about that there will be ternary system. Ternary system actually is that system which involves two components of the feed and one component which is externally introduced, one solvent. So we also talked about the various stages involved in liquid extraction, that initially you have to mix your feed with the solvent, and then in next stage after mixing you give them some time for the settling, like two phases are separated, and then you go for further treatment. These two phases which are separated are called extract and raffinate. So one which is with low density, that's called extract, and the other one which is with high density, that's called raffinate. After that we talked about this something related to solvent. So solvent is very important when you are going for liquid extraction, and the solvent should be such that it will attract only the solute, the specific component which you want to remove from some specific feed, right? As now you are aware about the basics of liquid extraction, so now we have to move further, and we are going to start with liquid extraction equipments. So in this topic I will introduce you with the liquid extraction equipment and their classification. Actually we are going to discuss the equipment which are used on large scale, industrial scale. Actually we have discussed yesterday one small piece of equipment which is used on lab scale, that was separating funnel, and we said we have to just shake it, mix it, and then we separate two phases. But here we are going to discuss industrial equipments, then we have to start further discussion in detail. So we will start with the mixer and the settler, first type of equipment, and then there are spray, packed, and tray columns, and we have to move further. I think by next lecture we will finish these equipments, and then we will move towards design of these liquid extraction equipments. Right, liquid extraction equipment, when you look at these equipment, as I told you that in the lab you can, what you can do, you can just mix your feed with the externally induced solvent. As you have seen in the figure yesterday, there was one funnel that is called separating funnel. You just shake it either by installing on an equipment which can vibrate it, or you can just shake it in your hands and then place it back to some stand, and there are two liquid layer which are settled. But here on industrial scale, in most of industrial application we use multi-stage counter current contacting. Multi-stage, yesterday I told you guys that multi-stage actually refers to more than one stages. If you remember, there was one slide which I have shown you that actually the solute which you want to extract from the feed, which is a part of carrier, and you want to move it towards externally induced solvent, so that is not totally transferred in one stage. So usually you go for more than one stages. So due to this he is referring here multi-stage. But then there is something called counter current. We didn't come across this yesterday, so we have just seen that there is small vessel and in which you are introducing something. But here counter current, you know that when two things are moving in opposite direction, opposite to each other, one species moving from top to bottom and other from bottom to top. Now this is suppose like one column or a vessel in which these two are moving in opposite direction. They will come in contact with each other and mass transfer will take place. Mass transfer in terms of that solute will be transferred from feed to the solvent. So now it will depend on their density, like which one will be moving in upward direction and other one in downward direction. Definitely we will be looking for more better contact, so we can adjust the flow. Most of the time definitely heavy feed will be introduced from the top and lighter from the bottom, so lighter can move upward and heavier can go downward. So this is counter current operation. This will be majorly part of the all of equipments here, hopefully in liquid extraction, where you have like counter current contact. Similar type of contact you have already seen in the absorption as well as in distillation. If you remember, that vapors are moving towards the top and liquid is moving from top to bottom, and they come in contact with each other, and that maximizes the contact between two streams, right? Here in liquid extraction equipment, two forces are very important. Just one, like gravity. Gravity is important because at the end of the day we have to settle down these phases which are coming in contact, and then we have to separate them into two separate phases so that we can go for further treatment. So as well as there is centrifugal force. I think we didn't discuss this yesterday, but centrifugal force is used because after mixing you have mixed these two, and maximum mass transfer has taken place. Later now you have to separate them into two phases. So in order to go for those two phases, one was gravity. Just you give them some time, you introduce this stuff to some vessel, and if you give them some time, definitely after some time they will be separated due to gravity difference. But if gravity difference is not much, then there will be problem, they will not get separated. Definitely will get separated, but it will take too much time. So in order to save time, maybe you can use centrifugal force. So by the help of centrifugal force, when you apply centrifugal force on something, so they get separated based on the force being applied on those objects. Just look for formula of centrifugal force. So if you remember, there was something mass in its formula, centrifugal force, from FSC class, hopefully you remember. So mass of any component, if it is higher, definitely more force is applied on this, and definitely that will be thrown away, and other which are they will be separated actually based on this mass when you apply something in centrifugal force on these phases. So this can also be used, but most of the time we are using gravity settling actually in liquid extraction. So when you generally look at liquid extraction equipment, there are two type of design by which effective multi-stage operation is obtained. What are those two type of design? First one, stage-wise contactors. Stage-wise, it means they will consist of stages. There will be one stage, like there will be mixer, and then there will be settler, like or separator you can say. So mixer and settler. So in such kind of equipment in which the equipment include a series of physical stages in which phases are mixed and separated. So just recall the lecture of yesterday. So there I have shown you something in the form of either it was I think in the form of bullocks. So if you remember, there was a mixer and then settler. I have shown you there one equipment of two stages, so mixer and settler, then there is mixer and settler. So these are stage wise contactors. There is one stage in which mixing is taking place and then settling is taking place, then there is mixing taking place and settling taking place. Why we are going for this? To improve the extraction efficiency. So other type of equipment are named as differential contactors. So in this kind of equipment, actually the phases continuously come in contact with each other, and they are separated only at the exits from the unit. For example, we will look at these in detail definitely, but here you can consider that there is some vessel in which contact is taking place, and then from same vessel separation is going to happen. If you remember one example of acetic acid extraction from water yesterday, so there was one extractor, and that was only one vessel in which we said they are coming in contact with each other, both feed as well as solvent, and from that same vessel extractor, from the top one phase was leaving and from bottom one phase was leaving. So such kind of equipment are actually differential contactors, in which they are coming in contact with each other, their mixing is taking place as well as separation take place in the same kind of equipment. So they don't have different stages like a separate mixing and then separate separator for settling of two phases. Further if we look at these equipment, so mechanically agitated or centrifugal devices are preferred, especially if many equilibrium stages are required. For example, your separation is difficult and it requires many stages, so usually in such kind of devices you are you usually use mechanical agitation. Mechanical agitation means you will apply some rotor, some motor with blades, and that will cause mixing inside this system, that will cause agitation in the system for the better contact, more contact of two phases which are coming two I can say liquids, like one is feed and other is your solvent. So when they are coming in contact with each other, just when you will mechanically agitate them, you will shake it, you will just introduce some rotation inside this with the help of like impeller, or like maybe sometimes you can go for centrifugal device. Like in centrifuge, what we do, we just move something with the high speed. You don't introduce here like impeller, but you are just shaking your vessel at the high speed, or you are just rotating it at high speed. So that will also cause agitation here and will improve contact between two phases, and with the help of this, definitely more better mass transfer will take place. So during passage through extraction equipment, one phase, yes, this, when you look at the phases inside these liquid extraction equipment, both are not continuous phase. One is dispersed phase. Dispersed phase is called discontinuous phase. Discontinuous, something will be when it is in the form of droplets, like one is introduced in the form of droplets and other is in the form of continuous phase. So with the help of this, definitely the contact is improved. We will discuss in next slides that how it is improved. So this somehow helps us to improve the contact. So one will be definitely in the form of discontinuous phase and other is in the form of continuous phase. Just you can imagine it like in the distillation, when we go for this, one is liquid phase and other is vapor phase. So vapor are like somehow in the form of these droplets, are dispersed phase, discontinuous phase. So that's help us to improve this mass transfer. I have downloaded one video, so I will just share with you in this group on Google Drive. So just watch that one when you are looking at this slide. So at this sense, you can just stop the lecture and go there. So you will see clearly they have introduced some lab scale equipment. I think that's pilot scale, so in which you can clearly see this, that's help us in improving the mass transfer. Okay, in static extraction column, there are something called dynamic and static. You are already aware about these statements. So something here we have discussed, mechanically agitated. What you are doing, you are just introducing with the help of some impeller, with the help of centrifugal force, you are just moving something. So that's called dynamic or agitated. And other one are like static extraction column. Actually these are static, I can say the equipment is static. Definitely your liquids will be moving here. One will be moving from top to bottom and other will be moving from bottom to top. Suppose if it is like vertical column, so definitely they will be moving. Static or dynamic here mean equipment assembly. So if there is some motor and that is rotating impellers inside an equipment, so that's the dynamic one here. But static mean some column is there is no like moving part here. So in static extraction column, they will be in the form of spray, packed and sieve trays, which we have to definitely discuss today, inshallah. So it is preferred to disperse the phase of higher entering flow rate. So in such kind of equipment, it is preferred that you disperse higher entering volumetric flow rate, the stream which is with high flow rate, that is preferably dispersed unless the other phase has high viscosity. Actually here what I can say, that if you are introducing two streams, one is feed and other is solvent, the feed which has high viscosity, usually we prefer that should be dispersed. Why? Definitely when something has high viscosity, if you disperse it in the form of small droplets, definitely it will improve its contact with the other stream. So if something is highly viscous, definitely if you don't disperse it in the form of droplets, that will start moving in one stream and that will make less contact with others coming across this or surrounding it. So I think you have already studied this fluid dynamics, fluid mechanics, so you are already aware about this concept that if something is highly viscous, definitely that will start moving in, I can say, like in streamline flow. So you know that in streamline flow there is not like good mass transfer as well as heat transfer, so we go for some turbulence. So here when something is with high viscosity, definitely we will just break it in the form of droplets, in the form of disperse. How will we will break it? That's the topic of later discussion. So that if it is like dispersed in the form of droplets, it will definitely improve the mass transfer. Okay, one thing I want to mention here, I am teaching from the same book, Cedar's book, 4th edition. So you guys can go to book if you want to read further. I will even advise you to go through this book. After this slide lecture, just quickly go through the book, because I am not only using this book, but the major content is from the same book, because I'm also bringing some content from other books. But if you just go through this book, it will be good for you. As well as we have to move forward, definitely you have to solve the problem, so just it's good to get familiarized with the book through this chapter. Right, this is first type, mixer settlers. So mixer settlers are one kind of equipment, we can say dynamic type. So in these kind of equipment, what you will have, as its name indicate, there should be some mixer and then some settler. Yes. In first part, definitely we will go for mixing of two liquid phases. When two liquid phases are first mixed in a vessel by one of the several type of impeller or agitators in the mixer. This is one some kind of vessel in which there are a large number of impeller or agitators, and they create agitation. Due to this, mixing will take place between two liquid phases, and after that they are mixed. We ensure that when they pass through this vessel, they are mixed, and then after that what you will do, you will give some time for the settling. So for settling, definitely we have to give some time. We introduce it to some vessel which is just like empty, and if you give some time, after some time, two separate layers are formed and they are extracted and raffinate. You already have seen for yesterday's lecture, like it was taking place in the vessel. That was something on the lab scale, but here in large scale, definitely inside tank, inside vessel, this separation will take place due to gravity. But as I told you that when gravity is not helping, for some cases you go for centrifuge. So in centrifuge, what you will do, you will introduce this mixed phase, and when you apply the centrifugal force, they will get separated. Okay, this kind of equipment, mixer settler, look like this. This is actually only mixer here shown to you in both of these figures. So just look at this equipment. This is from your book. Here what has he shown, that like feed in. Actually feed in, here you are introducing both feed as well as solvent from the bottom of this equipment, and you are rotating it. There is variable speed drive unit. Drive unit is like motor which is connected to this shaft, and on this shaft there are impellers, which he is calling it like turbine. So like turbine blades, you can say. So as we have blades in the turbine, so here these are the blades or impellers. So there will be these impeller attached to the shafts, and as well as you have some compartment spacers, like here we have some constantly fixed units. So here if liquid can pass through this path, definitely it will go to the top without good mixing. So what we do, we just provide them these stoppers, you can say. So with the help of this, it will just definitely come in contact with these rotating blades, rotating plate and turbine blade. So with the help of this, better mixing will take place, and then this liquid leave from the top, here emulsion out. So after this, you will definitely bring it to some vessel. So this is from your book, and this I have just taken it from the website of one company which is providing these equipment. At the end of the lecture I have acknowledged them, so here you can check from where it is. So here in this you can see that this is again mixer, but here the difference from the first one is that you have, like in this you are bringing rotating disc contactor, and in this contactor you have same type of assembly, but here liquid which is heavy phase and the other liquid which is like lighter phase, they are separately introduced into the equipment. So in this kind of equipment what will happen, they will come in contact with each other, but at the end of the day they leave separately. So in this equipment actually they are doing both, like mixing as well as settling. So when they are coming in contact with each other, here mass transfer take place. Something is heavy, so when this is heavy mean actually that will have more higher density, so heavier will definitely move towards the bottom and it will be like collected from here, and the other is like lighter one is being introduced and that will come in contact with the heavier one. Mass transfer will take place and that will leave from the top. But in the one which is shown in our book, that has separate, definitely when they are coming in contact together they get mixed and they leave together, we will need some separate settling vessel. So this is from one company which is providing, so definitely they have they should have better design, so that with the help of this definitely they are saving the cost of like settling vessel, so they are performing both tasks in one same vessel. So here again you can see from this portion that there are the walls of this, then there are something called compartment spacers, as we have there in our book. So there is rotor or the turbine blade, rotating blade, anything you can call it, like impeller. So they are connected to the shaft and shaft is rotating with the help of motor. So with the help of this mixing will take place, and this mass transfer occurs and finally you get separated to phases. So these are different kind of impellers provided in your book. Definitely there is not much detail about all of these, but they are various types which are used in industrial columns. And this is settling vessel. In this vessel you can see this like horizontally placed vessel. You can have either vertical as well as horizontal vessels. So in this vessel emulsion is getting in, actually emulsion which was getting out from this our first mixer, that will get into this. Due to this he call it like emulsion in. So there is some plate, I will just discuss this in next slide. So what is the purpose of this plate, and then there is separation taking place, and at the end of the day you see when this is the large vessel, something which was in the form of emulsion coming here, and then if you give it some time, definitely it will start settling out into two separate phases, and at the end of the day you will have one light phase that will leave from the top, and other heavier phase that will leave from the bottom of this settling vessel. And then there is from some tap for if froth formation takes place here, and if you want to remove it, just you can open this tap and can remove froth. Okay, before we jump towards this settling vessel, like here you have seen that there are some impeller which are introduced inside the one equipment, and there is some separate vessel, dedicated vessel, mixer, and that contains impellers. But sometimes if dispersion is easily realized and equilibrium rapidly approached, what does this mean? That if you are bringing two liquid, one is phase and one is solvent, you are bringing them in contact, and their contact can take place easily, mass transfer can take place easily, you can reach to the equilibrium between those. So these are actually such kind of liquid which are of low interfacial tension and viscosity. If their viscosity will be low, definitely they will make contact with each other easily. So in such kind of cases you can use some simple you can say simple structure or equipment, like you can go for inline mixing devices. Inline mixing devices mean inside the line, suppose there is one pipeline through which these two liquids are passing. So if you just pass them together through that line, and I mean there is some like orifice or venturi type structure inside this, so what will do it, definitely when there is orifice or venturi, it will create some turbulence there, and due to that here mixing will take place between these two. Next one, here you can sometime you can introduce them together to the centrifugal pump. You know centrifugal pump inlet, so at the inlet of this centrifugal pump, if you bring these two together, feed as well as solvent, so they will get mixed when they pass through these centrifugal pump. Definitely there is impeller, there is turbulence inside this. So like actually this is very simple equipment which is being used for this mixing. As well, sometimes you can go for the injector. Injectors are actually used for creating vacuum. So when you will create vacuum, one liquid is passing here. Actually here again we have some structure like you have in venturi meter. Yes. So like venturi, there is area difference. Like suppose you will have one structure in which area is changing. So when area is changing, definitely you know that velocity changes, and these kind of structure are used for creating vacuum in, maybe you know, with vacuum distillation column we create with the help of ejector. They call them ejectors. So ejector or injector, they are used for like creating vacuum. So if one liquid is passing from here, that will create vacuum, and if you introduce other from here, so they will come in contact with each other, and due to this turbulence their mixing will take place. So this is only possible when there is low interfacial tension as well as viscosity. But mostly in industries this is not so simple. These are just very simple, like you can say they are in replacement of like one impeller inside one large equipment, as you have seen here. So that can be like replacement of one impeller. But when we have to go for industrial operation, good separation, definitely you go for such kind of sophisticated equipment. Right, next is like settling vessel here. So that's you have already I think seen yesterday. There was something called decanter. Decanter is actually this vessel which separate two liquids if they are just in the form of mixture based on gravity. So decanter are gravity settling devices. So they can be vertical as well as horizontal, as I told you. So here this is the horizontal one. So in this you can see something called impingement plate here. So our baffle, impingement baffle or plate, maybe you have already studied also this in heat transfer. So here in separation process or this equipment, the purpose of this plate is, you see here, if you don't place this, just imagine for a minute that you don't place this plate here, so what will happen? Yes, new emulsion enters from here, and that will disrupt, that will come directly in contact with something which was settling here, so that will be pushing it. In order to avoid that push, we just place this baffle. This is just one sport to avoid direct contact of this somehow settled stuff with the unsettled stuff which is coming inside this vessel. So this is used to avoid the disturbing gravity settling process. In such kind of equipments, what we are doing, just we are going for something called simple density based settling. So we are not applying any external force, only gravity is there. So in this case, if there is very strong emulsion, as we are saying here, emulsion is taking place. From where this stream is coming, this is coming from settler, in which we have passed the liquids through harsh force of like mixing them. So if sometime emulsion is very strong, a major problem here is emulsion in the mixing vessel occurs due to intense agitation. You know that with the help of rotor, those blades, you go for intense agitation. So if this mixing is vigorous, too high, so it leads to like dispersed droplet size below 1 to 1.5 micrometer, and in this case very strong emulsion is formed, and you have to give too much time, and sometime even with time even you can't settle these into two separate phases. So in order to avoid this, definitely sorry, so when you go for design, definitely you have to look for this, that how much you have to provide the force, how much agitation should be there, so you don't go for strong emulsion. So in that case, if emulsion is taking place, definitely this gravity based settling is not going to help us, so we have to look for some alternative option, and that can be like something like centrifugal or maybe other. Yes, in these cases, in this case, this case which we have problem which we have just discussed, so this is related to this. So if strong emulsion is taking place, so in such case definitely not gravity, then external force or treatment will be needed to separate them. Another problem here which occur in such kind of system which are actually mixing and settling system, that is if there is small density difference. In such kind of equipment, if there is small density difference, already I think I have discussed it 2 to 3 times, so that didn't get settled due to gravity. So in such case you have to go for definitely other option like either centrifugal or maybe some other way to separate them into two phases like extract and raffinate. Right, this was something called up to here which we have discussed, mixer settler. They are mechanically agitated, or you can call them like somehow dynamic devices or dynamic equipment. So here these are the static which we have just seen few slides back. First one is spray column. So spray column is simplest device, and which is used for like extraction for being used for a long time. So you can see here, this is again from the website of same company, the figure which we have seen in last slide. So here you have one vessel, simple vessel, in which what you see here, you are introducing one light phase from the bottom, and other in like heavy phase from the top, and that is sprayed actually. So here what you are doing when you are spraying this heavy phase which is entering to this system, just think over it. A few slides back we have discussed it, that in these equipments of liquid extraction, we introduce the phases in the form of two forms. One is continuous phase and other is dispersed phase in the form of droplets. Like this one is being introduced in the form of continuous phase, light phase, and other heavier phase. When you are spraying it, actually you are introducing it in the form of dispersed phase. So when you introduce it in the form of dispersed phase, other is like this liquid coming in, so they come in contact with each other. By the way, here he has just shown these some kind of strips or plates, but they are spray column, are actually, I think this is just showing that liquid is coming in contact, but there is nothing inside such column. They are just spray column. They are just vessel in which you spray and you introduce, and they are coming in contact with each other. There is nothing like plates or anything. They are a separate column. We will discuss like plate column of those. So here either you can it is not necessary always to disperse heavy phase or the light phase. Sometime you can go for dispersion of heavy phase, sometime you are going for like light phase dispersion. As I discussed earlier, that it depends sometime on the viscosity, that which one should be dispersed. And by the way, one thing here, just ignore this part of like timer and air liquid. This is actually company equipment. They have shown exact equipment which is supplied, so this is not of our concern, this part. So droplets dispersion at the inlet, as you have seen that at the inlet, how you disperse with the help of one nozzle. Spray nozzles are not one, there are various spray nozzles. So with the help of those spray nozzles, you disperse this liquid. Okay, these are, as they seem, very simple one. And what will happen here, when you pass them through this, definitely these are the large vessels, so the liquid are coming in contact with each other, and at the end they leave, heavier is leaving from the bottom, and by the way, lighter one leaves from the top. So these kind of equipment, what do you think, can we apply for very good separation? No, definitely your answer will be no. But why? Because You are just bringing the liquid in contact with each other and they are leaving, so mass transfer will not be that sufficient. Although when they come in contact here, definitely this solvent which you are introducing, that has good affinity for some components of the feed, so it will take with this I'm just considering here, for example, that this is solvent and this is my feed which contain more than one component. So this will have good affinity for few component of feed, so it will take them away with them, but some will still stay inside this stream of heavy and they will leave from here. So due to this, they are sometimes used for those applications in which we are just looking for very small separation, like only one or two stages are required, like here it is mentioned. The other problem here which you come across actually is back mixing, axial dispersion or back mixing. Just hopefully you are aware about this, but just I will tell you quickly. So back mixing is something, if like, okay, as I said, this is the solvent, this is definitely moving towards upper direction, and other this heavier feed which we said the feed is coming towards like downward direction. So we just consider that suppose this solvent, when it was passing from this point, it will pick or it will attract some components from the feed. Just consider, for example, this is some organic liquid and that attract benzene. So when it will start moving towards top, this benzene which it has attracted from the feed, that can be again released towards the feed. That is called back mixing actually. That is actually back mixed with the original stream from where it was coming. At this point it was transferred to this liquid, to this solvent, but after some time, when it moves towards top, it gets attracted again towards some component of the feed and it goes back there. So this is called back mixing. I think you have already studied also this one in like reaction engineering. So back mixing is something came in the form of product, goes back to the reactant. So this same takes place here. This is figure from your book, in which you can see two different columns, like there is heavy feed as well as light feed. So what is the difference between these two figures? You can see here, this is dispersion nozzle, or like you have seen this spray nozzle. So this is again here dispersion nozzle. So in this case you are just dispersing actually your liquid, light liquid or light phase, and heavy phase will be continuous. But in this case we are dispersing heavy phase and light phase will be like continuous. Right, as I said here, this is very simple column, only spray column, in which like you do two liquids are coming in contact with each other and they don't give very good separation. So this can be improved with the help of some modification. And what is that modification? In the form of pack column. Hopefully you already remember pack columns. You have discussed, I think, in distillation, and we discussed them in detail when we have discussed this absorption. So pack column are simple vessel which consist of some packing inside that. So packing there are packing beds, like here you can see packing bed, two packing beds. So you have designed these equipments in absorption, so you are aware about this. So what we are doing here, this is one simple pack column in which there are packings, and you see definitely in such kind of system, either they are spray column or if they are like these pack column, these are such kind of equipment which give mixing of the liquid as well as settling inside same vessel. If you recall, we have seen this like static vessels. In static vessel, mixing as well as are static equipments, mixing as well as separation take place inside same vessel. Like here, they are getting separated, and again here, like definitely they will get separated. They come in contact with each other, they are moving in the opposite direction, counter current direction, they come in contact with each other. The mixing takes place, and then at the same time their separation also takes place, because the heavier one will move towards bottom and lighter one will move towards top. So they are separated into extract and raffinate phase. How this helps actually to improve mass transfer? Axial dispersion which was taking place in spray column can be reduced here somehow. This is not simple, like only two liquids are not there. There are some a restriction in between. So this somehow helps to improve that axial dispersion or back mixing. Back column help us to improve that problem. Not can't eliminate totally, but it can reduce as compared to the previous system spray column. As well, it improve mass transfer. You already know that if there is only empty vessel and two liquid are coming, they are in contact with each other, so they don't go for very good mass transfer. But when we introduce some other structure like this packing, you know that packing are introduced to improve the contact time and mass transfer. You already know about this. So with the help of this, definitely mass transfer improves. So when mass transfer will improve, this extraction of some component which we were supposed to improve from feed, or to remove from the feed, that will be improved. That will become more part of now this solvent. So here any kind of packings which we have already discussed, various type of packings in the previous chapter of absorption, they can be used only you can't use ration ring. So just look for this, why we can't use ration rings. So I will advise this, go back, look what are ration rings, how they look like, and then you can get the idea that why we are not using ration rings here in such systems. Okay, one important thing here, if you recall, just can you recall what kind of packing material was there? Like there were some different types, but there were also different materials. Quickly maybe you can recall, there were metal, there were glass, and there were plastic. These were different material. Maybe there can be another material, but I can just recall these three. So just think about those, that when you were using those different materials, if you recall, it was told that they provide different type of wettability. Some of those provide good wettability, like there is proper dispersion of the liquid on the surface of this, and some didn't provide very good wettability. So just think over it, that what kind of packing material you will be looking for. Definitely such material which can provide good wettability, because with the help of this, when its surface of packing is fully wetted with the continuous phase, so definitely it will provide good mass transfer with the dispersed phase. So if it is not wet, definitely liquid disperse as well as continuous phase, they will be just moving as they are moving in the spray vessel. Although definitely it will be a better contact as compared to spray, but if material is good, that provide good wettability with your feed, so with your continuous phase, either it is feed or a solvent, so that will provide good mass transfer. One thing, like as we said, in spray column they can be used for 1 or 2 stages, but these can be at least used for few stages. More than 2, 3, 4, like you can use them. So stages if you calculated that you need like 2 to 3 stages in like dynamic system like impeller and settler, this is that one. So that can be achieved in only one vessel. You don't need to install separate like mixer then settler, mixer settler. So you go for calculation, and if you get those stages, and then you can use this equipment. Then definitely based on those stages, how much you have to transfer the mass, and you will select the equipment. I think this is the last type which we are going to discuss today. That's the sieve tray column. Just look from where we started. We started with these static equipment, simple vessel, spray vessel. Then we applied packing, and then next that is sieve tray. Somehow you can link it to the same like we have discussed in distillation or absorption, that there are packed as well as tray column. So this is one type of tray column, the sieve tray column. So in this you can see here, you already know its structure, that there is a column and that contains some trays, and they are sieved, they have holes. So again in this column also counter current contact take place. One will be entering from the top, either feed or a solvent based on its density, as well other will be entering from the bottom, either feed or the solvent, which will be lighter one. So they just here you can see again what you can observe from here. They are the nozzles. So what does this show? That this solvent is being introduced as a disperse phase, and other feed will be coming here in the form of like continuous phase. So continuous phase and disperse phase will come in contact with each other on the surface of these plates, in between these plates, and majorly on the surface of these plates, when there will be like continuous phase liquid, and this will be coming in the form of droplets, so that they will come in contact with each other, and separation will take place. So at the end of the day, in the same vessel, again here, their contact also takes place, as well as they get separated from this vessel, like heavier leaves from the bottom as a raffinate, and lighter one will leave from the top as extract. So sieve trays reduce axial mixing, and promote a stage-wise type of contact. Actually, axial mixing is a problem, as we said, in the spray tower as well as pack tower, so that is somehow more reduced in this kind of system in the sieve trays. By the way, as I have told you in last lecture, that he said this is quite mature technology, but not that mature, like we can't prove many things from the equations. They are based on experimental data. So maybe you will be thinking how it is improved, like axial mixing here, an equation didn't support it. These are all things based on various experiments. So disperse phase here, which is analogous to the vapor bubbles in the distillation flow up the column with the redispersion on each tray. You remember from the distillation as well as from absorption, that vapor move towards the top of the column, and they come in contact with the liquid on the surface of plate. So same here, a disperse phase, as we said, disperse phase here, our disperse phase is like entering from the bottom in this case. So they are in the form of like bubbles, as we said, like you can say analogous to bubble, not specifically in the form of bubbles, but they are like droplets. So droplets like start moving towards top, and liquid is coming from the from top to the bottom, so they are coming in contact on each tray. Heavy phase is continuous, flowing at each stage through a downcomer. So a similar phenomena as you have seen in distillation column, that this is the liquid, so it moves from the downcomer and then to the next plate, and again to the downcomer, and so on. And then across the tray, like it moves across the tray, like it will be moving on the surface of tray, and there is a wear definitely, and then it like overflows from this through this downcomer to the next plate. Overall, based on experience, it is seen that if you design them properly and operate them, so these are very good for extraction, as compared to the two static devices just discussed before this, like packed as well as spray column. So they perform better than them. The reason behind that is because disperse phase droplets, they just break and reform on each tray. When they will come, they will pass through the holes. What will happen? Definitely due to some resistance, that can be broken, that droplet can be broken, and when again it leaves from that plate, it will be again formed. So due to this, when it is broken, definitely better mass transfer takes place. So sieve tray extractors are subject to some limitation. And what are those limitations? As we are saying here, that they are very good, they can be used in a better way as compared to the previous ones. So but still they also suffer some problem. And what are those problems? As they are looking like distillation column, so they will be like definitely facing same issues as distillation column face. So those issues are like flooding, entrainment, as well as to some extent weeping can also take place here. So you are already familiar with these kind of terminologies. I don't want to just again repeat. So if you just forgot, please go back to either distillation or absorption, and you can see their definition. So these problems are some part of the sieve tray liquid extraction column. Yes, an additional problem is froth formation. Froth formation also takes place, we have discussed in absorption as well as from the distillation, but again here that same problem takes place here. And what will be due to froth? what is the issue of froth? Just think over it. So when froth takes place, that the contact between two phases reduces. When froth takes place, like the contact of liquid and vapor is reduced. Actually, on small scale, if you remember from absorption, there was froth formation, but if it is extensive, too much froth is taking place, so then there will be problem. As I mentioned in the lecture in few minutes back, that there is one video I will upload. So in that video you can see like continuous phase, disperse phase, as well as you can observe such kind of problem. They have shown like flooding, entrainment and froth formation. You can see there somehow. That's it. So up to here what we did discuss today, we have discussed initially liquid extraction equipment, why they are needed, how they work, and then there is their general classification. As we said, they are in the form of something called mixing and settling devices, or we can call them like dynamic devices, and then there are static devices in which both mixing and settling takes place in the same vessels. The three equipment we have just discussed at them. And we discussed mixer separator system. Actually there is some mixing unit, and then there is a separate vessel in which maybe gravity based separation or based on any other mechanism separation will take place to get extract and raffinate phase. Then there are spray column and packed and tray tower. These are static examples of static devices in which liquids are coming in contact with each other. They are moving in counter current direction, and finally their contact takes place and they get separated. And when we started from spray, as we keep on moving towards like packed and tray tower, we said that their efficiency is improved, but still they all face some kind of issues. At the end, I would like to thank this company, Think Coach Modular Process System. So they have provided those colorful images. I have downloaded from their website.